All right, welcome to section 5.5. What we're going to be covering here is just some more identities and formulas for you to memorize and utilize in different ways. So we're starting off with sort of the most important from this section, and that is the double angle formulas. Double angle formulas is what allows us to rewrite something like the sine of 2 times an angle, the tangent of 2 times an angle, or the cosine of 2 times an angle. So you've seen these in section 5.3 bookwork, where we would solve for sine and then divide everything by 2. But depending on the problem, we might need to apply this formula just so that we can rewrite things in the first place. So you can see here the sine of 2 times u, where u just represents some value, can be rewritten as 2, the sine of u, the cosine of u. The tangent of 2 times u can be written as 2 times tangent u over 1 minus tangent squared u. And the cosine of 2 times u has 3 different options of how it can be rewritten, all of them equally correct. It's just that they're different iterations and they might be used in different scenarios. So the cosine of 2u can be written as cosine squared minus sine squared of u, 2 cosine squared u minus 1, or 1 minus 2 sine squared u. Any of those 3 work, and again, it sort of depends on the situation. I am going to do a little bit of the examples just because the notes are pretty short and I want to get you to understand some of it. So 2 cosine x plus sine of 2x. Now, if I'm going to solve this, I need it to be one trig function first. And what I can do is rewrite this. So I have 2 cosine x plus, this is the same as 2 sine x cosine x is equal to 0. Because that's our sine of 2. This is really like our u. So 2 sine of u, cosine of u. At that point, I can see that I can factor out a 2 cosine x. And what I'm left with is 1 plus sine x equaling 0. Now that it's written as factors, I can set each one separately equal to 0. And then solve using all of that 5.3 knowledge that I have and maybe don't like. So here I get cosine x equaling 0. Here I get sine x equaling negative 1. And with each of these, I'm going to reference separate unit circle drawings. So cosine being 0 happens here and here. These points are equidistant, which means it can be written as one solution. I start with the smaller angle, pi halves. And since this is only pi units away in both directions, it's going to be pi halves plus n pi. Sine x being negative 1, sine x being negative 1 happens just here. So that would be x equaling 3 pi halves plus, I'd have to go around a full circle, 2n pi. Now, the only thing about this is that this solution is already something that will come right here from this equation. Which means, yes, this is like a separate set or a separate answer for this factor, but you're getting all the same solutions that this one is already giving you. You're not going to get any new solutions from this equation, which means it's not needed. So just one equation for this. All right, moving along, I want to do one of these examples too. If the cosine of theta is equal to 5/13, and we're looking from 3 pi halves to 2 pi, which is telling us that we're in the 4th quadrant, then find the sine of 2 theta, the cosine of 2 theta, and the tangent of 2 theta. So if I wanted to draw this, I know that I'm working in the 4th quadrant. Cosine is 5/13, which makes this third side negative 12. Sine of 2 theta, remember that is the same as 2 sine theta cosine theta, where here is theta. So that would be 2 times the sine of this angle is negative 12/13, and the cosine of this angle is 5/13. When I multiply this all together, I get negative 120 169ths. Doesn't reduce. The cosine of 2 theta, I'm just going to use the first of those formulas, cosine squared theta minus sine squared theta. So when I'm doing cosine squared, I take the cosine, 5/13, and I square that, minus I take the sine, negative 12/13, and I square that. 5/13, when I square that, I square the top and bottom separately. So that gives me 25 over 169 minus negative 12 squared gives me 144 over 169. So when I subtract this, I get negative 119 169ths. The tangent of 2 theta, you can use the formula. However, in this case, it's actually wiser not to, because we've already found the sine and the cosine. Remember that what tangent is equal to is sine over cosine. So this will be the sine of 2 theta over the cosine of 2 theta. So in this case, it's not wise to use the formula because we've already found these two things. We would just have negative 120 over 169 over negative 119 over 169. The 169s cancel, and I'm left with 120 119ths. All right, we'll skip a little bit ahead and go to the power reducing formulas. So power reducing formulas are a way of rewriting something like sine squared u, cosine squared u, or tangent squared u. Now, something to keep in mind is that these do not always have to be used. They can be. And depending on the scenario, you would or you possibly wouldn't. We've done plenty of problems already where you've solved stuff that had sine squared, cosine squared, and tangent squared, and you didn't use these in any way, shape, or form. These apply to problems where all of a sudden, for some reason, I can't solve it because there's some other trig function blocking me. So I'm going to have to rewrite the sine squared or cosine squared or tangent squared. So I get 1 minus cosine 2u over 2, 1 plus cosine 2u over 2, and the tangent squared is just the quotient of these two, 1 minus cosine 2u over 1 plus cosine 2u. We'll do that example in the examples video, and then just half angle formulas. So half angle formulas, again, they're not something that has to be used. They're something that in certain situations you might need to use, but we haven't always needed to use them. So this is for the sine of u over 2, cosine of u over 2, and tangent of u over 2. For sine, you get plus or minus the square root of 1 minus cosine u over 2. For cosine, you get plus or minus the square root of 1 plus cosine u over 2. And for tangent, you get 1 minus cosine u over sine, which is also the same as sine over 1 plus cosine u. These are equivalent expressions. So that's all we're going through in the notes. I did a little bit of those examples so that you have some of a frame of reference. In the rest of the examples, I'm going to go over those other slides where we're going to use half angle. Here we're going to use power reducing, and this is probably one of the roughest examples that we do. And then just a little bit more of that double angle stuff. If you feel like you're fine with it, just go ahead, start, try and answer that homework, or jot down if you have a question that's going to have to be asked.